Unfortunately, there's a little bit of a problem with telescopes. They're stuck on Earth. So they have to look through the atmosphere. Well, that's a little bit of a problem. Some of the EM radiation doesn't make it through the atmosphere. It's completely blocked out. Sometimes heat can distort your radiation, right? You ever see a hot day and it looks like there's water on the road? Heat is distorting the light. That can happen in the atmosphere. So you don't want to be anywhere it's hot to get a good view through a telescope. Also, dust can block it out. Other things in the atmosphere can block out light. And atmospheric turbulence, usually caused by heat or wind, but they can make little swirls in the atmosphere that then hurt your light as it comes in. So when light passes through the layers of air, the different layers have different densities. Different densities means you have bending occurring. Right? And I believe Dr. Phil talked about how the spoon in the glass of water looks like it's bent. Right? Obviously it's not, but that can happen with the light coming through the atmosphere. It's a different density, it bends. And this is why stars twinkle. Twinkle, twinkle, little star. Yeah, it's not twinkling. It's actually just the light coming through the atmosphere and hitting atmospheric turbulence and some refraction from different densities. That's what's making your star twinkle. Sorry, I know I just ruined that song for you. Alright, so what do we do about these problems? Well, again, if we're stuck here on Earth, we need to get telescope to a cold, high place. And that's why I kind of pointed out where the telescopes were on a mountaintop. Because it's getting as much away from the city, right? So heat and light distortion. And it's getting up into the air. As you go up in the air, your temperature decreases. If you've ever gone anywhere where you've went up a mountain, you would know that there's snow on the top of the mountains in the middle of the summer, even though it's 90 degrees down in the valley. So it's on a mountaintop where it's cold and there's no atmosphere or very little atmosphere. You're trying to get away from the atmosphere. If you go up Pikes Peak in Colorado, there's a gift shop at the top of it. I know it's kind of cheesy, but they sell t-shirts that say "Got Oxygen," because up there it's harder to breathe. There's not as much atmosphere. There's not as much oxygen. So that's a good place for a telescope. So the telescopes are actually in southwest U.S. in Arizona. There's an observatory. Hawaii, Chile, I had mentioned those before. All on mountaintops, several thousand feet up into the atmosphere so that it gets away from as much as possible. Well, there's another solution to getting away from all that. Don't be on Earth, right? Space-based telescope. Not only is there no heat and no dust and no light pollution and no atmosphere, it can also collect all of the EM radiation. All of it, because there's no atmosphere to block it. And the most famous one, the Hubble, right? Launched in 1990. It gets above all of the atmosphere. It can collect anything. It doesn't have to worry about light. It doesn't have to worry about heat. It doesn't have to worry about dust. So here's a picture. On the one side, you can see the scientists assembling it. And I mean, look at that pristine mirror. That's just gorgeous. On the other side is actually a picture. I got to go to the Kennedy Space Center, and they have a replica of the Hubble. And so that's one of the students that came with me. standing in front of the replica of the Hubble. Also, I would just like to point out that the Student Government Association at Brandon does a really good job of putting on a lot of field trips. And so this was one of them. The students got to go for free and they got lunch for free. So it was kind of impressive. Here's some pictures that the Hubble has taken. Some planets, some galaxies, some nebulas, some stars. It's just pretty impressive to look at those pictures and think those are actual pictures, okay, copies, but still actual pictures taken by a telescope in space of somewhere deep in our universe, not even in our solar system, some of them. And you're sitting here at your computer looking at it. These are actual pictures from space. All right, so the Hubble Space Telescope, positives of it. Well, it orbits high above the atmosphere, so it's not affected by the atmosphere. It can look at wavelengths, EM radiation wavelengths, that the atmosphere would absorb. On the other hand, it's really hard to operate. You can't just go up there and be like, oh, I do this, so, swing it around and point it at that, right? Yeah, a little bit hard to operate. And if something's wrong with it, which there has been stuff wrong with it, how are you going to fix it? Oh, well, we'll just crash it into the Earth and redo it all. Yeah, probably not, right? You have to get out there to fix it, so it's really hard to fix. And half of the sky is blocked by the Earth, as you saw in the first, where the Earth, the Hubble, and then the deep space. And you can see it's going to be blocked by the Earth. It's orbiting the Earth. So a little bit of a limited range there. The other bad thing, it orbits the Earth fairly quickly. Which means if you see something interesting and you want to stare at it for an hour to collect as much data as possible, yeah, good luck with that. You're going to have to wait till it goes around again and get it for a few seconds, maybe a minute or two, and then goes around again, and then another couple minutes, then goes around again. And so you can't really sit there and stare at anything. With the technology that we have today, we can actually do some really fun things with telescopes, not just look through them. Right? We can actually look at the images as they're being taken, and we could make adjustments to the telescope so that we can get rid of any distortions that might be there. Right? How? We can adjust the temperature. We can adjust for bad seeing. We can get better airflow in the domes. And we can move the mirror to get a better picture. That was called active. Now this is adaptive, which for the sake of the test, if you mix them up, that's fine. Or just call them active or adaptive, whichever one you choose. But adaptive optics can actually correct for the atmospheric turbulence and change the way the mirror is shaped. How does it do this? The telescope shoots a laser out of it. That just sounds cool. What it's used for is not quite as cool as saying the telescopes can shoot lasers. Anyway, we know the specifics of the lasers. We know the exact peak of the brightness of the laser. We know how straight it should be, all that fun stuff. And so we can look at the laser and see if anything in the laser is being distorted, and if so, by how much. And so we can assume that the rest of the light is being distorted by that same amount and change the mirror, change the airflow, change whatever in order to get a better picture. So by doing active and adaptive, the resolution of telescopes on mountaintops are actually comparable to the Hubble space telescopes. Pretty incredible.